Hello, my name is Shashank Sharma. Today I'll be presenting my work done under the guidance of Professor Anurag Purwar at Stony Brook University. The title of research is A Machine Learning Approach to Solve the Alt-Burmester Problem for Synthesis of Defect-Free Spatial Mechanisms. Let's start by defining the Alt-Burmester problem. The Alt-Burmester problem involves calculating mechanisms whose coupler can pass through a given sequence of poses and path points. The pose constraints are defined by their positions and orientations. So that's going to be x, y, z coordinates and the roll picture, while the path points are only defined by positions, so x, y, z coordinates. The well-studied path synthesis and motion synthesis problems are special cases of the larger family of Alt-Burmester problems, and thus it serves as a more general framework to work with. The name Alt-Burmester comes from researchers Burmester and Alt, who pioneered work on motion synthesis and path synthesis problems. Now let's talk a bit about the kind of spatial mechanisms we want to synthesize. In this paper, we focus on synthesizing spatial 5SS mechanisms, which consist of a rigid floating link called coupler, supported by 5 legs, so these 5 here, and each leg has a spherical joint on both the ends, and that's why it's called 5SS, S standing for spherical. Although we synthesize only 5SS mechanisms, the proposed algorithm is general enough to be used to synthesize any single degree of freedom spatial mechanisms. An intrinsic characteristic of single degree of freedom mechanisms is that they have multiple branches and circuits, as you can see here. So you can see multiple branches here, multiple circuits here. For a synthesized mechanism to be useful in practice, all poses and path point constraint need to lie on the same branch and circuit. This is because to switch between circuits, a mechanism need to be disassembled, while to move from one branch to another, the mechanism need to pass through a singularity position. Thus, we want to synthesize only defect-free mechanisms, since those are the only useful ones. Let's also briefly talk about variational autoencoders, also named called VAEs, which is a machine learning model we use in our algorithm. It is a generative model which consists of an encoder network and a decoder network connected by a low-dimensional probabilistic latent space. The variational autoencoder has 3 properties which makes its use really attractive for us. First is its property to do data augmentation. We use a VAE to learn the relationship between the orientations and the path positions of motions. It can then be used to add compatible orientation information to an Alt-Burmester problem and kind of convert it into a motion synthesis problem, because we now have orientations and path information for each location. Second is the variational autoencoder's capability to give us a variation of motions. So it will give us multiple motions for a single input, and that helps us synthesize multiple mechanisms rather than a single mechanism. Third is the dimensionality reduction due to the bottleneck layer between the encoder and the decoder networks, represented by the latent space Z. This serves as a low-dimensional signature which can be used to easily compare coupler motions and use an atlas-based approach to find solution mechanisms. Here we see the complete algorithm. As you can see, it's divided in 2 phases. One is the training pipeline and one is the inference pipeline. The training pipeline is run once to train the VAE and create a labeled dataset using latent signatures. Once the training is complete, the inference pipeline can be used to synthesize multiple mechanisms. Let's dive deeper into the training pipeline. So the first step in training pipeline is to create a database of pure defect-free motions of 5SS mechanisms. We accomplish this by selecting arbitrary 5SS mechanisms and simulating their forward kinematics using a Newton-Raphson based solver, and this gives us pure motion which is defect-free. In the paper, we simulate 10,000 such 5SS mechanisms and calculate their coupler motions, which result in 10,000 coupler motions. Next, we process this pure motion data to make it better suited for machine learning purposes, and multiple operations are done in this stage, like data cleanup, normalization, balancing, augmentation, and data masking. And as a result, we end up with a motion plus path database. So this one has some motion, has some poses and some path points in it, which represent Alt-Burmester problems. This database has 400,000 such curves in it, and we use it in the next step, which is training the variational autoencoders with these two data sets we have. One is with complete motions and one is with partial motions. Once the variational autoencoder has been trained, the encoder network can be used to generate latent signatures, and which can be used to label these databases. Since the signatures are low dimensional, they help make database search for similar motions really efficient. This completes the training phase, and then we can move to the inference phase. During the inference phase, the user inputs a sequence of poses and path points representing an Alt-Burmester problem. These are then normalized and fed to the encoder network, which generate multiple latent space vectors. And these latent space vectors are sampled from the underlying distribution sigma and mu here, which represents family of feasible signatures. Next, we then query our database to find similar signatures and find solution mechanisms. Thus, we can synthesize a family of 5SS mechanisms for an Alt-Burmester problem. Alternatively, we can also use existing motion synthesis approaches, since we do end up with a variety of generated motions. So, for example, for 5SS mechanisms, there exist algebraic and optimization approaches in literature which can be used, and we can also generate multiple solution mechanisms using existing approaches. Here we see an example of the algorithm in action. We input a sequence of poses and path points and are able to synthesize multiple 5SS mechanisms here as shown. In the figure, the blue lines represent a single rigid coupler link. So all these blue lines are a single link. The gray lines represent binary links, and there are 5 binary links represented here in each mechanism, and the triangles represent the fixed pivots here. And yeah, that concludes the presentation. For more details, please check our paper listed below here. And thank you.